So, yeah, welcome back, everyone. I want to now start the lecture from our proper about Motivic sheets. So, yeah, all this business of Motivic sheets comes from the work of Morella and Wygotsky, and they introduced the stable motor category. I'm trying to give an exposition of this beginning. So, let's say the first chapter is the stable motor category, which is called H, and in there we will now spend some time about Motivic spaces. Yeah, so for those of you, I mean, you did see, I guess, this lecture by Simon Pengal in the opening school. I don't know if what exactly he said, but roughly speaking, you can think of these Motivic spaces as being the analog of space and homotopy theory, and this would be the analog of spectra. But of course, now it's done by geometry, so it's not that simple, but sort of that's roughly speaking where this lives. And yeah, and as I said, this is due to Morella and Wygotsky. In the case of somehow finite dimensionalized schemes. And then there's various extensions in all kinds of directions. So I want to mention especially the work of Ali Khan and also the work of Haiwa, among other papers. So this has really been revisited many times. And most recently it has been revisited by Remy Tubac, so the Tubac who was here, and Wolf, and so they pushed this a little bit further even to allowing to somehow mixing the classical theory with Boyta sheet. And what I will do is I will sort of push it even a little bit further to something that contains what they did, and yeah, close. So anyway, let's start. So yeah, first of all, we have to do a little bit of real algebra in order to set up sort of the machinery under the hood. So I remind you a Euclidean pair is a pair of a ring H and a line such that for all finite A algebras B, there is the following thing. So we have the ideal coordinates of this B, and we have the ideal coordinates of this B1I, and we want this to be bijection. Yeah, that's what the definition of NC appears. When A is a local ring and I is the maximum idea, then this is exactly the usual definition of NC in a local ring, or its equivalent, let's say. So, and in particular, when A is the complete local ring with respect to the topology defined by this maximum idea, then this would be an example. Yeah, but this definition makes sense. And it's important for us also in the non-logic case, and that's what we will use to define the next thing. So a map, let's say A to B of commutative rings is called weakly smooth, respectively weakly et al. And if the following is true, if for any and C impaired and C, I, we have the following listing condition. So we have this map from A to B, and we give ourselves to read the diagram like so. So we have now go back into this quotient, and so if let's do if for any and C impaired and any commutative diagram like so, there is a lift. So there exists a lift. So this would be in the case of weakly smooth, respectively. Let's say there exists a lift, respectively. There exists a unique lift like bracket. So that's so weakly smooth means existence of a lift, and weakly et al. Means there is only one lift. And so there is a fact. Yesterday we talked about rather talked about weakly et al. and he used the definition of by Scholz, which is the following: that we can say that A to B is weakly etale in that sense, if and only if B is flat and also the map the diagonal map somehow. This is also flat. Okay, so that is the definition that we see in Bad Scholz, for example, and this equivalence here is due to De Jong and Olander. So relatively short but non-trivial paper shows that we have this condition. So we will freely use both points of view, but yeah, I think that's also a nice perspective, and of course it gives rise to sort of letting let us drop the unicity, and that gives the weaker notion of weakly smooth. This notion of weakly smooth seems to be not much studied. It does appear in some recent paper, but hasn't been studied all that much. So let's collect a few properties. So I'll just say them very briefly. So I focus on weakly smooth, but most of the statements are also just exactly the same for weakly etale. So weakly, maybe I write W smooth, yeah, in the sequel just to save some chalk. W smooth maps are stable under composition and also under push-outs. Yeah, by that I mean if I have a weakly smooth map and I take some other ring map and then the push-out is again going to be weakly smooth. Okay, so then and this is also for weakly etale. Just the same property, so that's okay. Next thing is that what is the relation between weakly smooth and weakly etale? So A to B is weakly etale if and only if it is the F is weakly smooth, and the diagonal. So let's give a name to this. So I call this delta F here. So it's really just sending B and B prime to E times B prime. I use this diagonal because if we pass the seams, this would be the diagonal map. So F is weakly etale, if only if F is weakly smooth, and this diagonal is also weakly smooth. Yeah, this is how they relate. And then so if F is weakly etale, then this diagonal is also weakly etale. And so far this is sort of yeah, this is what it is. But here's a key interesting thing. If F from A to E is weakly smooth, then we have the following thing. Then there is a commutative diagram, and it's false. So we have this original map that we are given, and then there is the polynomial ring over A with respect to this set B, so that's a humongous big polynomial ring. And then there is a certain tensor, which I will comment on in a moment. And then here is a certain natural map vector. So, and then we have a map this way. And I will comment on what it is. Yeah, so maybe for the moment, just accept it like that. So this, once again, this is the initialization. So this H is the initialization of this moment round. This is the initialization of this big polynomial ring with respect to what ideal, with respect to the ideal given by the kernel of this map. So the kernel of this map from A adjoint B to B, right? So we have such a general map which is onto, it has a certain kernel, and the initialization with respect to that is what we consider.
Could you review the board on the right?
Yeah. And so in particular, our map F is a retract. Now if you look, so this is the map F, this is the other somehow slightly more welcoming map, you might say, and this is a retract of this, of A mapping to this initialization. And you will later see why that is a crucial thing. So for the moment, we can think roughly the role of these guys is kind of a little bit like in classical homology, you have this notion of standard smooth morphisms, which are étale over an affine space, and here it's pro-étale over some infinite dimensional space. So that is going to be very useful later on. Okay, now I have to erase something here. Okay, and the other comment that I should make is what is the relation of this weakly smooth, in comparison to the somehow more usual conditions. So we have the following. So we have if F is smooth, then it is weakly smooth. And that in turn implies that it is formally smooth and also flat. And these purifications are not reversible, but they are reversible if F is in addition finitely presented. So this holds if F is finitely presented. Okay, so in other words, for finitely presented maps, these things all agree, formally smooth, weakly smooth, smooth. But well, this is clearly much, much weaker than this because let me see. There's no finiteness, and that is also there's also examples showing that that doesn't know in general, doesn't work in general. Okay. So in other words, you want to think of these weakly smooth as being, at least from my point of view, the correct generalization of smooth if you drop all finiteness condition whatsoever. So that's the statement. So the proof is, let me quickly say it. So this first thing here is formal because it follows from basically this lifting thing. Yeah? So if you have a push out, for example, of this A to B, you think A prime to the tensor product, then you will still have this lifting condition. That is formal. This thing here is also formal because here you ask for, in this on this point here, you ask for existence and unicity of lifts. So this gives you existence of lifts, and the existence of lifts with respect to the diagonal forces it to be unique. Yeah? So that's again a general categorical nonsense fact, which doesn't use anything about these particular reads here. What about statement number 3 there? So this one, I say if F is weakly étale, then this diagonal is weakly étale. Why is that? So we will use this here. So if F is weakly étale, then the F is weakly smooth and the diagonal is also weakly smooth. And to see the diagonal is weakly étale, we need to see that the diagonal of the diagonal is again weakly smooth. Okay, so maybe for this part here, use part 3. We'll use that the diagonal of F is an IC. Yeah, so this again has nothing to do with the sensitivity and so on. This is just because it's we are in an ordinary category. So this is what's called one truncated. But anyway, that is also formal. This next thing that is also formal, I want to explain in more detail because I think that's sort of interesting. So part 4. This really also follows from the definition. So let's look at our map A to D, and then we have this map into the polynomial ring, and we have this map. Okay, that's fine. So I call this pi, and again I call I this term of this pi. Okay. So I can consider the initialization of this ring with respect to this. This is what I call H for initialization. Okay, this has the following property. So this is a general property of the sensitization that if I do the initialization of that, of that ideal, then I will get this quotient. You will again be B. Yeah. So in some sense, the cancellation doesn't affect, in some sense, what the expression phi is. Yeah. So that's property of cancellation. Now, so far we have not yet used anything about the original map. Now we do. So this is by construction a Henselian pair, or well, this is this here, not that. Yeah. So this is a Henselian pair, or I'll rather maybe I should say this is a Henselian pair, and that's the quotient of this mod that. And so by definition of weakly smooth, we get such a map, right? By very definition, and that tells us what we want. Yeah. So okay. And what about this? So I think I will mainly just say this is somehow well known. If you look up the sex project, for example, smoothness are known to have this lifting property against Henselian rings or Henselian pairs, and also weakly smooth versus formally smooth. Why is that? Well, formally smooth is this lifting against C versus C mod I, where I square is 0, right? And that is in particular a Henselian pair. So that's why it holds. And the flatness follows from this here, because you see this map here is the retract, like I said, of that one. So it will be flat if that one is flat here, this one. But that is, you see, this big polynomial ring, which is certainly flat, and then this hensellization, which is the pro-étale thing, and that's also flat. Okay, so that's why we flatness comes about. Okay, and if it's finally presented, then it's known that formally smooth and finally presented equivalent to smooth. Yeah, so that's that's what we have. So okay, this is sort of we will, unlike Morelli-Gorski, who took smooth schemes over a base scheme as the geometric building block, in some sense we will rather look at these weakly smooth, at least if we want to. And this lemma somehow tells us that they behave to a certain extent similarly as smooth varieties, smooth maps over the base scheme. There is one caveat. I don't currently know the following. So, caveat or question. Given A to B, such that the composite to a bunch of localizations, so such that these are all these are all weakly smooth, and let's put a product here. So that this is faithfully flat. In other words, this is Zariski covering. Given the Zariski covering of spec E by this guy, such that the composite is weakly smooth, I don't know whether or not this implies that A to B is weakly smooth. Yeah, so that is this is known for weakly étale, as we reviewed yesterday. It's also known for smooth, and it's not clear to me whether that holds for weakly smooth. But I will somehow say, okay, I don't care. I will only ever really consider that definition in the case of affine schemes, and I think that still works well. Yeah, as we will see. But yeah, if you have an idea about that, that would be interesting. But even without that, it works, I think. And so here is the next key statement about these weakly smooth things. So let A be a ring, and I an ideal. And then we have the following. We can look at weakly smooth A algebra, so that's my notation. And by what I said, we have this stability under pullback, so we can send such an algebra V to B mod I, and this will be again weakly smooth. Okay. And so let me call this maybe I star. And what I claim is then the image of I upper star generates the target category under retracts. Yeah, so in other words, every weakly smooth A1 algebra is a retract of something coming from A. That is the lemma here. So why is that? This combines what we did earlier. So it suffices. So it suffices because we know that all these weakly smooth things are retracts of these standard guys. It suffices to consider something of the form, let's say, yeah, here is B in the notes, which is better because I used the B here. So let's say I write C there. So let's say B of the form A mod I adjoint some set and then some initialization. It suffices to consider this and with that. Well, what can you do? If you did not for this initialization, well, you would just, of course, take the polynomial over that set. And so the extra thing is the initialization here. And this is, however, in Bad Scholze, for example, and also in the text project, it appears the statement that, yeah, so let me, yeah, let's say that way the initialization of any int etal, in this case, A mod IS. So it's not really relevant that it's A mod I adjoint S, but rather that it's the quotient of something by an ideal. But anyway, the initialization of any such int etal algebra is again an int etal algebra. Is an int etal S algebra. So you can initialize and you keep the property of being int etal. And not only that, but that, so maybe let's give a name to this. So the initialization of any int etal algebra, I don't know, maybe D. And so I call this I write it like hence D. So this is now an int etal A algebra. I can tensor over A with A mod I. And I get back my original algebra. Okay, so that's what they prove. And so that tells you, okay, this B here, you can initialize and get an int etal algebra over this, and that is a polynomial algebra, and that is, of course, weakly. Yeah, because these polynomial rings, they have all the properties. Yeah, so now observe. I mean, this is trivial that A adjoint S is weakly smooth over A, right? So I remind you this the lifting condition was we have this A, then in this case it's polynomial ring, and then here a quotient map. But mapping out of here just amounts to picking a bunch of elements, and so this you can sort of do along the surface. Yeah, so this is fine, and the int etal is like I said, saying that I mean it's in particular weakly etal, and so we are yeah, so that's a key thing, and this is going to be somehow the commutative algebra aspect that makes this work eventually. And there's a similar, I mean, this lemma is similar to the fact that appear also in the context of just etal or simple map, so it's not completely somehow coming out of the blue, but the fact that we have that we allow these weakly smooth things actually gives us much more freedom in the sense that, otherwise you wouldn't be entitled to consider such a thing if you insisted that you want to lift, let's say, smooth maps to smooth maps, but that's something that we can do. Okay. All right. So this is a little bit of commutative algebra. And now, as I said, we want to get towards the definition of these Motivic spaces. So there are two inputs. One is they are sheaves, and we have a little bit of freedom for what topology exactly, and they are a one invariant. And I want to first talk about the sheaf aspect. So let's say I call this little this here grow Motivic and grow etal sheaves. So what I'm trying to do is to give an exposition that sort of reduces to what has been classically done. So that would be the non-pro part. And there you have, again, this standard or étal, which you can choose. Some is better than the other for different purposes. And then there is the pro version of that, which will also see. So here's the definition first. Yeah, so let's say S is an affine scheme. So for a certain time, we will just consider affine schemes, as I said, and we denote by W S M. And so I guess at some point I have to drop this here on the blackboard, but in the notes at least you find this. So W in quotation mark in parentheses SM as echelon is the category of affine schemes, affine S schemes that are weakly smooth over S. Okay, so and I guess at some point I will just not write these parentheses anymore and just maybe here and there say there is the sort of the version with the without the weak. But okay, anyway, that's what we have. And now we want to put a topology on that. So when we consider Motivic, yeah, no, sorry, let's do this in a different order here. So let's let's first define the topology. What are these topologies? So we can do this in different generalities. So let's say we can consider schemes for any scheme S, or we can consider these weakly or not weakly smooth affine scheme over S where S is affine. And we can also consider the somehow small side, if you like, so consisting of these weakly étal schemes over S. Yeah. So anyway, let's fix one of these categories of schemes that we want to consider, and let's say what is this pro is there for this especially. So here is the definition. So the pro research topology on this category C there is the topology, the coordinate topology generated by Zariski covers. Okay, and the following covers. There's first of all something that I keep forgetting, namely the empty covering of the empty set. It's like 0, okay, the boring. But okay. And then the family of the following form, so maps the following form. So spec A localized at a certain element plus spec B mapping to spec A such that so the condition now is the following such that so here we have spec B, spec A. This is supposed to be this is supposed to be a weakly étal map. Okay. And the condition is that in here you look at this basic open subset. Okay, and here we have pre-image. I don't know that's not so relevant for the moment, but anyway, this is what we have there. But the condition now is that on the closed complement, this is supposed to be as follows. This is the experiment. Right? So it's so we basically allow all weakly étal, but we insist that away from some such basic open subset, it's a isomorphism. That's the condition. And so if I say not weakly étal, but rather étal, then this is exactly the definition of this Motivic topology. Yeah. So as it appears, for example, in Bachmann-Wolvers paper. Okay, so far so good. That's the Coordinate image topology. And the Floyd topology, of course, is the one just consisting of covers like these things. So this is by Schotze, the Crow et al. Topology is generated by heuristic covers and the reflective maps set V to set A, which is weakly. That's how. Okay, so all right, and so I want to write a sheaf tau on C. So C is one of these categories of schemes, and sheaf tau C for the category of sheaves, the infinity sheaves. Yeah, this is the infinity category of sheaves. So of animal, if I don't specify anything, so with respect to the top. Okay. So I just want to point out, for those who don't want a hypersheet, is I don't insist on power. I don't want that. I just really want a sheet coming. Yeah? So practically speaking, if something is a sheet, if, for example, if you're to check this, you evaluate f on A, f on B, and on this, and then you want this to be a Kohlbeck diagram. And that's we'll actually come back to this in a moment. Yeah. So that is that's what's meant here, and not hypersheets, but rather just sheets. Okay, so example. Well, it's a bit uncanny. We saw much of this already yesterday, but I do want to briefly say this again. If we have a field extension, then this is an entire cover. If and only if this is finite and separable, it's no entire cover. If it is, if and only if it's separable, and it's in this image cover. Never, I mean, not never, but only when it's an isomorphism. Yeah, because sort of, I mean, yeah, sort of this condition doesn't allow you to do any actual extensions when you want to have a cover. So there's a more general fact, which I maybe just say orally. So these Polish image covers, they have the property of being what's called completely decomposed, which means that when you have any k point where k is a field in here, you will always be able to lift it up to your cover. Why? Well, because here, I mean, sort of here it's clear, right? So if the point lies in the open, okay, then that's fine. If it does not lie in the open, then you, because of this isomorphism, you can lift it again. Yeah, so that's that's important.
And sorry, for this image, you mean really this image or also pro this image?
Okay, yeah, I could do pro this image, sorry. This image or pro this image. I always said so. Okay, good. So in other words, there's a certain, for the moment you can just say I don't care about whether I'm not taking pro this image or pro tal. Later on we will sort of play around with this a little bit more. Okay, good. So then the main example, of course, of the sheaves that we will look at are the representative sheaves. So notice all these maps, as I said, the weakly maps are all flat. And so in particular, we can use flat. So for example, for any scheme F over S, we have this representative sheaf, which I will call H at S of X. So this will just form over S of rank into X. So we can regard this as if we want to function from affine schemes to sets, or well, anima if you want, but here it's really not necessary. This is a sheaf for all these topologies, or topologies, because they are weaker than flat topology. And flat descent tells us that is the sheaf. Okay, so All right, so that's what we will use at some point, that we know how to sheepify these representables. Okay, the next topic I want to start looking at now is a handy condition on the property of being misnamed or pro-misnamed. So it turns out that there is a difference between this misnamed and tal and pro-misnamed and pro-tal because somehow, there is let's say, so there is a way of expressing the sheaf condition for these misnamed and pro-misnamed sheaf topologies in a way that only involves finitely many objects somehow. And this is usually called excision. Let's say excision versus descent. Here is a general abstract lemma. So, given a collection, so I want E of Cartesian diagrams of schemes or affine schemes or something like this. So A prime, X prime, X, F, so let's equal J prime, J, A, so like that. Okay. The names don't really matter so much, I guess, but anyway, given such a thing, such that the bunch of conditions hold, namely, first we want P to be stable under phase change. Okay, so what do I mean? So if I map from some other, I don't know, y, let's say, to the x, then I can pull back this entire diagram and I won't be the resulting diagram to be again part of this class E here. I then want this map J to be a one-mapping, in the sense of categorical sense. So this will be satisfied for these kind of open inverters. And finally, last condition is following. It involves these diagonals. So third condition, if I consider A prime mapping to X prime, so this is my original map there. And here now I look at the diagonals. Like so, and similarly like the other one, A prime, like this. So this is the prime. So this, for any such thing, this should still be. So that's what we require as well. Yeah. So basically, well, let's look this. Yeah. So in other words, in particular, this delta type has to be somehow nice as the F was in some sense. So these are the conditions, and we will see this in practice in one moment. Then now here's the conclusion. Then any, let's say that for a free sheaf, let's say F, so which is defined, let's say, on schemes or affine schemes, or any sort of category that allows you to form all these pullbacks. That's not really important here at this point. We're designing any scheme, so this is any infinity category. Could be chain complexes of integrand or anything, even infinity category could be relevant. And for a pre-sheaf, the following are equivalent. Condition one is the one that we care about, namely that it is sheaf, which involves the changing order of any color, then that's a priori infinite amount of thing. So for an equivalent, condition one is that for any square that's above, for any squares there, we can put y to be x plus x prime plus a. All right, so and then we consider the change nerve of this y happening to x, right? So this starts with y, then it takes y times y over x, and so on. And then we can look at now finally f of x maps to the limit in that infinite category C here, which is supposed to with units. We can look at f of y mapping to f of y times x y. So we have these two pullbacks, and then we have f of y times y times y, and so on, right? So that's something we can consider. So in other words, we consider sections of this pre-sheaf on y, which are compatible in the sense of, well, having being part of this limit on here, but then we keep going. Okay, so that's what generally happens. And that's why I said this is an infinite amount of data. So we want this to be an isomorphism. That's the condition, the sheaf condition with respect to this one type of map. And the much simpler condition is that now f maps any pullback square, maps any square in E to a pullback square in F, in C, in this category, in this Y category. Yeah? And so you see, so in other words, completely f of x maps to f of a, f of x prime, f of a prime, and we want the f of x to be the pullback of the diagram of the other three things. Yeah? So it's really just four objects that come up. And that is an easier condition, and this is called excision, or this condition. Okay, so that is a general abstract nonsense lemma, which I've included a reference for. I will not attempt to say much about it. It's not completely trivial, but also not for crazy as well. Let's use that. And we want to apply this to this coordinate image thing now here. Notice I'm erasing it, but this was weakly et al. This was global embedding. So that's the homomorphism, and this weakly et al. It's the condition here is that delta f is again, weakly et al. Basically, and that is what we saw earlier. So we will be able to apply this now. So corollary is let's say again, C is again an infinite category with all limits. And as affine, and then f is a functor, is a pre-sheaf of this category of weakly or not weakly affine S schemes. You see, so that's a pre-sheaf just, and then following our equivalent. This f is a sheaf for the pro or not pro, depending on whether I allow each include or not. This Motivic topology. And secondly, in this product image, we have this one condition that we have this empty cover, so that's something we have to still keep. So f of the empty set is the final object. Okay, this is boring condition. And the interesting one is f maps. Well, these distinguished squares here. So I forgot to write it down, but these squares that I just erased are called distinguished squares. These distinguished squares, again, to a fullback square. Okay. Good. So, right. And this is somehow, there is no similar such statement for the pro et al. Topology. There you really have to accept this infinite limit coming up, but for the Snapchat and Protus image, this is a little bit easier. And as an example, application of that, one can observe that example. So for those who know about K theory, I think we will review this later in more detail, but maybe I can still say right now. Let's say the function that takes an affine scheme and sends it to the so-called non-connective theory is a pro-Motivic sheaf because you can so you will want to check this excision, and so there is a, I mean, this is still not trivial, but so this excision is something that appears in this paper by Thomas and Jakob. Yeah, so one has to say something. It's not really true, but it is known that for for these diagrams that I erased with this open and this isomorphism on the complement, that one has a K theory of has the excision property. Yeah. So maybe I'll just say this here, and yeah, as an example, and we'll later somehow see other examples, but for the moment, it's an abstract example. So this is the Motivic pro-Tal or not topological aspect of Motivic's basis. And as I said, there is another one which is the homotopy invariance. Of course, inspired by the fact that its quality, the line is contractible, and somehow more or less the insight was, okay, if we force this affine line to be contractible by fiat, it turned out to have a very strong, very well behaved theory. So let's go in that direction now. So let's say this is the definition plus basic properties of Motivic spaces. Okay. So yeah. First, I have to say something about homotopy invariance. So let's say a pre-sheaf F on again one of these categories. So weakly or not, it doesn't really matter at this point. But anyway, so let's say one of these categories of smooth or weakly smooth schemes to some infinity for C again is called homotopy invariance. Invariant. If the expected condition is true, namely if f of x is isomorphic to f of a1 times x for any x, I mean for any object x that you consider here. Okay, so that's homotopy invariance, and the idea is, well, yeah, how to say it? I mean, where does this come from? Historically, somehow the insight was that one of the properties shared by many of these cohomology theories is that they are homotopy invariant. Yeah, last week I kind of gave a hand wavy, fake proof, you might say, into why entire cohomology is homotopy invariant when L is prime field characteristic. So that's one example. Then we have the cohomology characteristic 0, and of course classically singular cohomology and so on. So they all have this property, and so it made sense to somehow isolate this as a key condition, and somehow Motivic they kind of in some sense turn it upside down. They say, okay, we only ever consider these things, and it turns out if we do that, then you get a very well behaved theory. So let's do this in just one moment. But before I do this, I want to state one fact about what happens if we have a sheet that is not going to be invariant. So, for example, this K theory that I just mentioned is not in full generality homotopy invariant. It is homotopy invariant for regular rings, for example, but not in general. Yeah? And so, you don't always have the luxury of already having that. If not, you want to see, okay, what to do about it. Here's the lemma. So the inclusion of these pre-sheaves, so I write pre-sheaves A1 for those pre-sheaves that are homotopy invariant in that sense. So on this on these categories. Yeah, I'll see on something, but maybe I'll drop this. So I mean, this is true for any target category C. So let's think of anima for the time being. If you want to have something more concrete. And anyway, we have these inclusions of all homogenic invariant pre-sheaves into all pre-sheaves. Okay, that's this, and so this emits a left adjoint, which you can very roughly think of being a little bit like a sheafification, similarly to the fact that sheafification is the left adjoint of the inclusion of sheaves into pre-sheaves. So I call this left adjoint LA1, and this has a concrete sort of formula. So you take your favorite pre-sheaf and you want to render it A1 invariant in that sense of being and then the question is, what is it? So let's evaluate it on some scheme X. And what comes out is that this is the co-limit of f of not of f of x only, of course, but rather of f of x times delta n, where this delta n here is the algebraic simplex. So it's stack of z adjoint T0 up to Tn, 1 below T0 plus and so on, Tn equal to 1. So we have, and this forms the post-simplified scheme using all these inclusions, etc., like very much like in algebraic topology. And so you can evaluate your pre-sheaf on not just on X itself, but rather on all these simplices, which are abstractly, of course, abstractly asymptotic to AN. And this is what you get. Yeah. And so in particular, there is what you have to think. If this F was the map of was a pre-sheaf of sets or reading groups or anything in some ordinary category, then actually it suffices to stop here at delta 1. You don't have to do all this code. So what you do is you take sections on X and identify them if they come from a section on X times A1, and you identify the two somehow restrictions. Similarly to what we did for Jakob's. Okay, that's what this is, and so it has this particular formula, and this LA1 is a very nice functor. It commutes with finite products because of that formula. Yeah, so if you have a finite product of sheaves, then somehow this will commute with this cyclical limit, and okay. Okay, that's what it is. And so the proof is, it's pretty, but I don't want to include it just for reasons of time. So there is a paper by, I mean, this is classical. This goes back all the way to very Wygotsky, if not even much older, I think. But in any case, there's another definition in this paper by Antio and Motivic, for example, which really uses some geometry. Yeah, it uses somehow kind of the multiplication of A1 by itself and playing around with that. Yeah, that's yeah. This is how we can render a sheaf homotopy invariant if it wasn't already so. And maybe when I erase the board, I say that the Delan complex in derivative of 0 is homotopy invariant. But there's a funny thing: if you take the Delan complex in positive characteristic, if you render it homotopy invariant like that, it will be 0. Yeah, so it's, I mean, so it does something to. So there's in the notes I've included an exercise which is really a reference to a paper, but this can be worked out somehow. Yeah. Anyhow, now let's define homotopy spaces. Like I said, this combination of homotopy invariants and being a sheaf. So that S being FRC. And so now we will say we'll define for Motivic and guitar. I want to say the following. So then I write H of S for the how to say the full subcategory of free sheets on smooth affine schemes over this S that are tau sheets and also a one variant. Okay, so that's the definition of the velocity, literally. And for this pro version, there, of course, this doesn't really make sense to just look at smooth schemes because these covers will destroy the property of being smooth, and so there, what we do is we basically do the same thing, but we replace smooth by weakly smooth. All over the place and do that. Okay. No question? No. Okay. This is the category of Motivic spaces. All right. So this looks like a crazy beast, and it is a crazy beast. And what we will do now is start proving some properties which are the main thing. I mean, the main non-trivial property, let's say, is the motivization theorem for that. So, but before we go into this, I have to spend some time with some of the more, more or less trivial properties, let's say, or formal. It's maybe not trivial. Let's say formal properties. So here's the lemma. The first lemma. Right. So maybe let me just say for emphasis. So this H, I might write H tau if I want to emphasize the quality, and sometimes I don't really do that, but remember that for this image and tau, we really just look at smooth, and otherwise we look at these weakly smooth. Yeah, so this is always implicit in the choice of the tau. It's also implicit the choice of the site that we look at. Okay, anyway. So, and also maybe from now on, I will not always repeat this phrase let S be affine. Yeah, so for a certain amount of time, this S will always be affine. And I will not repeat it all the time. So, okay, here is now the following thing. So this H of S is a presentable infinity category. Okay, so that's a nice category. Now, more precisely, it is in fact an accessible. It is an accessible localization of this pre-sheet category of these weakly or not weakly smooth affine S schemes. Well, maybe write it once of anima. Yeah? So this pre-sheet for me always means pre-sheet anima. If I don't explicitly do something else, and then we have this HS, which by definition is a full subcategory, and being an accessible localization means this has a left adjoint, which is accessible, and this is called L mode for motivic localization view. If you want. Next thing is the technical property in this category. Co-limits are universal, so in other words, they commute with pullbacks in some sense. And then there's something that only holds for Motivic and Motivic, but not for the Etal versions. Then this there is a stronger grip on that due to this decision type statement. So two statements here. This H of S as a subcategory of the pre-sheet category. This one there is stable under filters limits and also under finite products. And therefore compactly generated by what? By basically by representative sheets, or rather their typical localizations. So it's compactly generated by what? So by, yeah, let's call this M, with appears down here only. Anyway, M S of X, which is this L mode of this H S of X. Value this H S of X is really just basically the X, regarded as a representative pre-sheaf. It happens to be the sheaf already, okay, but anyway, then we still have to render it homotopy invariant, and so we apply the cell mode to do that. And the claim is this is the compact object in the Nisnevich case or pro-Nisnevich case of this category H. So generate by this for all weakly or not weakly smooth F9 schemes. Okay. Okay, that's good. Yeah, maybe one additional thing still under the assumption of Nisnevich or pro-Nisnevich is that this L mode can be computed by doing the following. So you basically do what you think you have to do. Namely, you first render your sheaf A1 invariant, okay? Then you think, maybe it's not a sheaf, so let's force it to become a sheaf. But then it might not be A1 invariant anymore, and so you keep going. So in other words, what you do is you basically iterate this more and more times and apply this to your sheaf. Yeah, so yeah, that's what you can do. And I don't want to. So may I just say orally briefly what's going on here? So this first thing is really a generality about sort of localizing a pre-sheaf category in some sort of objects. That is, Guri gives this to us. I have up to the caveat, which I haven't commented on yet, that these categories of weakly smooth schemes, they are not strictly speaking small categories. So if you want to be precise about that, you should have included some cardinality bound on all these FN schemes. I will just simply not even care, but you have to do that if you want to do it sort of. I mean, yeah, if you want to do it right, but I'll just on the blackboard, I don't want to mess with that. So anyway, that's the generality. This second thing is also a generality about localization. So I'll refer you to the notes for the reference. And this one here is, I mean, not as formalized as these ones. So it does use this, the fact that we can check this sheaf condition for Nisnevich and pro-Nisnevich in terms of this excision. And that tells us this stability under filtered colimits, right? Because if you think about it, you have a filtered colimit of, let's say, Nisnevich sheaves. You want it to still be a Nisnevich sheaf. Well, what you check is you have this finite excision condition. That's a finite operation, and therefore this will commute with this filtered colimit, and that's why. Okay. So that's coming from there. And once you have that, the fact that it's compactly generated follows from this. Yeah. So what I'm saying is this inclusion here preserves, it's stable under filtered colimit. So in particular, this preserves filtered colimit, and therefore this preserves compact objects. And in this pre-sheaf category, all these things are compact. Okay. Well, this is all relatively formal if you somehow dig up the right references and use for this one here this excision. All right. Good. As a remark, I want to sort of not let you forget this special fact about these really smooth things. So for tau being equal to pro-Nisnevich and pro-eta, I want to state the following. I want to state this H tau or H into S is generated under colimits and retracts by what? By what kind of particularly nice objects? By the motives. I mean, like what we call this motive, yeah? So M stands for motive. By the motives of X, where X is, so let's say, S It's the S stack A, and this X is that of form A adjoint some set B, which may have come from a ring earlier, but anyway, and then some installation. Yeah, so we have this particularly nice class of generators, which are these kind of standard weakly smooth polynomial. Yeah. Well, this is coming from the fact that this was true for these these categories of these smooth things in the first place. And there is a similar effect, which I will not comment on much, in the case of the non-pro things. So there it's a little bit more tricky because you don't have this freedom of doing this initialization, but still there's a related effect which sort of is necessary to run the proofs for the non-pro things. Yeah, but in some sense we will see that what we do for these pro topologies will actually be in some ways easier than for the non-pro, because we have more freedom of more just simply more objects basically. Okay, good. So we have these nice generators which we will use later on, and what we will also use later on is the following universal property. So how do you map out of this H? We can ask, and here's the following thing. So let's C be a presentable, presentably, maybe other to say, presentably symmetric monoidal infinity category. Yeah, presentably means it is presentable, but on top of that, it's also supposed to be symmetric monoidal, but on top of that, so the tensor product should be equivalent preserving functor. So that's what this little y here encodes. So if you want, you can say C is the commutative algebra objects in PRL. And if you don't like this symmetric model, you can also just say presentable, but then there is a weaker universal property. So now here's the universal property. So functors that preserve colimits and are symmetrical model out of this category HS into your favorite target category C, for example, spectrum might be an example. Functors out of there. If you have such a functor, then of course you can compose it with this L mode, right? You get certainly a functor from the free-sheet category, which you can then restrict to these schemes. So this is going to be a functor category from now weakly smooth affine schemes as before into C. Okay, so I consider this composite, and I claim this is fully faithful. So this is fully faithful. Then this is fully faithful, and the image is equivalent, or let's say consists of those functors, or let's say of functors f from these weakly smooth, or C such that f of x times a1 is always isomorphic to f of x, right? That's the homotopy invariance condition that we have imposed, and f is a sheaf with respect to this topology tau that we have this kind of implicitly in the English. Yeah. So this is why is that? Well, again, this is just sort of thanks to Lurie work now very easy. So this h tau was the localization with respect to this, with respect to the topology and this forcing it to become a1 invariant, and so such a localization. I mean, functors out of the localization are the full subcategories of functors out of this in this case, satisfying these conditions. And well, what are the colimit preserving functors out of the free-sheet category? These are just sort of, you know what such a functor does when you know what it does on represent. Okay.
But wait, this functor is composition with L mod.
Yes.
So instead of weakly smooth affine less, I should have three sheets of anima over.
Right. So there is an intermediate step, fun L from this free-sheet category, and that fun L from the free-sheet category is that. And I forgot one other thing, namely I want this to be, I mean, the symmetric monodic functor if I may or may not ask for that, but if I have a functor that sort of takes products of affine schemes to products in C, then this will jazz up to a functor, to a symmetric monodic functor out of the integral Motivic space. Okay. Good. Right. Again, this is relatively formal, and I have included some references. One question, please.
One question. Yes, please. And what? In the case of Motivic and pro-Motivic, is sheafification really necessary? Because we have the simple codings to preserve exceptions.
Well, it might not be a sheaf in the first place. Oh, you mean here?
And you apply LA1 to a sheaf.
LA1 to a sheaf. Is it again a sheaf? I think you have to do it because you think of it that way. So this LA1 basically asks you to understand in particular sections of f on x times a1. So then you have a cover of x times a1, which might not come from a cover from x. So I think you don't have a priority reason for this to be a sheaf. Okay, so the time. Oh, okay. I wanted to be somewhere else. I'm not physically not in math. Okay, anyway, let's collect the basic functors. So this is again very much similar like what we saw yesterday in Leonardo's talk about the touch. So this is again pretty formal. So let me try to say it quickly. So let f from T to S be a map of affine schemes. Okay, so then what we can do is we can consider weakly smooth limit over S, and we can take this pullback. This gives us again weakly smooth thing for T by this stability on the base change. Okay, that's good, and that introduces for us functor on the pre-sheaf categories, which is like exactly like yesterday, is the Khan extension along this thing. So in other words, this is the functor that takes the representable sheaf associated to some smooth scheme over S and takes it to the representable of the pullback. Yeah, so this gives us f upper star, maybe let's call pre-sheaf on this pre-sheaf category on here, the pre-sheaf category on there. And this has a right adjoint, which I call f lower star, which is really just pre-composition with this thing. Okay. And then, so this f lower star preserves the condition of being a sheaf and also being modularly invariant. So this preserves H. So in other words, we get a functor f on the level of these Motivic spaces. And it admits a right and left adjoint, admits a left adjoint. Adjoint, which is for the upper. And then the upper star is the Motivic localization of the pre-sheaf guy. So the upper star is L mode imposed with this upper star, is naive upper star, you might say. So this is the left adjoint from H. So that's GHG. Yeah. So this one you have to sheafify, generally speaking. And now, again, like yesterday we talked about the case when f is prolectar. Now here we have a little bit more printed, namely f is weakly smooth. Then we have a forgetful functor, which is the right adjoint, so we can forget. In the case of this weakly smooth, we take a weakly smooth T scheme and we just remember that it was also weakly smooth over S. And then we get a left adjoint. Yes, correct. Adjoint F lower sharp. Then HT to HS, which is characterized by you take some weakly smooth thing or not weakly over T and send this to MS of S. Yeah, so that's what that boundary does. And it's a left adjoint, so it again will preserve all co-limits, and therefore you know what it does on all objects basically by knowing what it does on these representatives. Yeah, so another way of reading that thing is such a functor. I mean, yeah, functor is specified by what it does on these MSs of these X's. Okay, so that is all pretty clear. So this is just very formal. And so I'm sorry, there's a bunch of formalities here now. But yeah, once this is reset, maybe. So let's see. Yeah. Next level is not only do we have this for every individual at F, but rather we can say the following. So we have there is a functor which I call H alpha star, just to remind ourselves that we talk about alpha star, or maybe like H alpha star tau. So it goes from affine schemes to PRL, and it sends such an affine scheme S to H of S and F to that alpha star. Yeah, of course, that is not sort of a good way of saying, or correct way of saying, of course, I cannot somehow specify a functor like that. But what I'm trying to say, there is a functor like so, whose evaluations are what we did earlier. Right? And so again, this is formal because, I mean, somehow you have to observe that, sort of eventually, well, of course, pullback of tau covers are tau covers and so on. Yeah, so I think I will just accept this here, and not only, yeah, but let's leave there. So that's all factorial, and then there's smooth base change or control smooth base change on this smooth on the situation. So smooth base change. That. So if we have the TPS, where this is supposed to be weakly smooth, well, weakly in the actually smooth in the molecular case. So let's say F prime G prime, and then there is a natural isomorphism. What can you do? You can do this left adjoint and lower sharp and then pull back, or you can do the other way around. Prime lower sharp E prime also. So there's an isomorphism like this. And if we want, we can pass the right adjoints and do it this way. So we can say first do G O star and then F star. Or again, the other way around. You can load star F star. Yeah. So this is a formal consequence of that. And that comes out of this universal property. So you have two functors out of the H of here into the H of there. Okay, let's try and check they are isomorphic. There's a priori natural net coming out of the adjunct, and it's invertible because you have to take it only on these where is it? On these motives here, and then you observe, okay, hey, this F lower sharp takes the weakly smooth thing over T, forgets that it was just remembers the S, and then takes the pullback, and then you can go the other way. And so it's again a very formal thing. Right. Okay, that is not terribly crazy, but then comes small extra bit which is useful. Namely, so you see one other way of looking at, oh sorry, I forgot. It's off here. One other way of looking at this first thing is to say this H is the pre-sheaf of categories or of presentable categories. And what's more, it's actually a sheaf. So this H upper star, maybe I write tau just to emphasize it here at this point, is a sheaf of presentable infinity categories for the topology tau. What do I mean by this? So i.e. if X to S is a tau cover of affine schemes, then HS will be equivalent to the limit of HX mapping, again using star pullback functors. So your upper star, let's say P1 upper star, 2 upper star, into H of X times SX. And so on. Yeah, so I emphasize you have to keep going. It's not possible to cut it out because it's an infinity category. But if you are willing to do that, then you have this equivalence. Okay. So it's a sheaf of such categories. Here I want to give an argument. So proof of 3. I mean, it's again pretty formal, but this is something I want to share. The thing is what? So let's say we call this map F here. So F is in particular smooth or weakly smooth. And so therefore this F upper star, which is coming up here, admits left adjoint. And so there exists this left adjoint that commutes with all pullback functors. Yeah, according to what I just said here. That's thing number 1. And thing number 2 is this F upper star from HS to HX is conserved. So here I'm using not only that it's a map, a weakly smooth map, but actually, the tau cover. So this is conservative. Why? Well, because you see, it's by virtue of that we have asked for the sheaf condition. Yeah? So something will be nice forms after pulling back only when it wasn't nice forms before, due to the fact that it's the color. And so this is conservative, and then there is a lemma or fact by Lurie, a bar back type. Bar back applies. And again, note there's reference applies to tell you this is an equivalent. Yeah, so that's a quick and easy way to check sheaf conditions. You want your pullback functors to be conservative. That you have to have, otherwise there's no way of this being an equivalence. And then on top of that, you need somehow that the left adjoint of these maps coming up here, they commute with all the pullback maps in some sense. Yeah, so there's a general such lemma. That is very useful. Okay. And so for us, what that means is that we have so far only defined affines, H1 affine schemes. But of course, now it's the Zariski sheaf in particular, not of them, of course, much more than that, but so that's also somewhat helpful. What do we want to do when we have a non-affine scheme later on? But that's what happen later. So now, maybe just a very quick corollary. So if J when U into S is an open inversion for the moment of affine schemes, then J lower sharp and J lower star are both fully faithful. Why is that? That's because of that by base change. So you have your U to S. Here you put U as again, then pullback is U again. So you can say push forward and then pullback will be the same as going this way, and then it's the identity. Yeah, so that's the general nonsense fact again using this base change. And the fact that these things are monomorphisms. All right. So you see, we are kind of slowly building up to basically all things that we saw yesterday about Koitachi. So this is kind of a small, easy part of that. And the last thing I want to say about sort of pretty some formal properties is what is going on with the monoidal properties. Yeah, let's do that. So then kind of a small strengthening of this thing there. So this H star, like I wrote here, is a Lex symmetric monoidal functor. So what do I mean by that? I mean, in particular, what are the mean? So we take two objects here and take their product and then apply H first, apply H and then take the product, or the other way around. And so what this means now is H of S tensor H of S prime. There better be a map from H to H of S times S prime. You know, this so and Lex means these maps, these functors just exist, but they are not equivalences, just a functor in PRL. And so only preserving both variables. And what is that functor? It takes such a module of some smooth or weakly smooth scheme over S. And another one here, and simply sends this to the product of these two schemes. Okay, which is again weakly smooth. Or smooth. Okay, that's what this functor does. So, and again, of course, now there is a little bit of formal work here to be done to say that this idea indeed jazzes up to a Lex symmetric monoidal functor. So, which I will not do here. It's at the end of the day boiling down to the fact that if you have, let's say, for example, a tau cover of things on S, and you take a product of something over S prime with it, it's again going to be tau cover and things like this. So there's no hard geometry convergence. So that's this here. It's a Lex symmetric monoidal functor. So let's parse a little bit what that means. Now let's kind of squeeze this line a little bit. What does it buy us? So this is what I'm saying now is very close to what we saw in Bastian's talk last week. So I think I will be kind of brief on that too. So remark, if we have given a functor, so I call it D here, so it's not because I only use a different somehow letter than this particular functor F here. Given a functor, let's say on affine schemes of PRL that is Lex symmetric monoidal, let's try to see what structure this encodes. Then we can do the following. Then I claim any D of S is actually a symmetric monoidal category. Actually. Why? Well, this is, I mean, there are two ways of saying this. So one way is an object S in here is always an algebra by means of a diagonal. I mean, algebra in the opposite category, so you can call algebra if you want. So such a thing will be mapped to an algebra object. So that's what this is. Yeah? So more concretely, you can say the multiplication is you first apply this exterior product, go to S times S, and then do the delta, the H of delta, which I will also call delta of star. And you then back in on here, right? So that's again the formal thing. And that gives the structure of symmetric monoidal. Why do I mention it here in this way? There's two reasons. One, as was pointed out last week by Bastian Klassen, this is the way that we will be seeing it also on the level of correspondences. That's reason number one. Reason number two is that if you imagine for a moment we already had the Schrieg functors, we could define a different symmetric monoidal structure, possibly, by doing delta upper Schrieg. Yeah? So in some sense, this box is in some ways the more fundamental thing than the tensor product relation. But okay, anyway, that's symmetric monoidal category, and for any f from T to S. This upper star is again a symmetrical functor. Okay, so that's fine. And again, sort of following from this thing here. So we have these full X are symmetrical model. And I want to then say, yeah, one last thing. The bells are ringing. Is it already 12? Yeah. Okay. So okay, one thing, and then I'll stop. Again, as a forward consequence of this, we have these so-called projection formulas, you might say. So we have f goes from T to S. We can say f is in d of T, G is in d of S. We have a natural map this way. Okay, coming from the adjunction and coming from the modality of the other star. This is just a map a priori, not in general an isomorphism. We will see this kind of the main thing that if this f is proper, eventually we will see this disintegrated isomorphism, and that will allow us to do it for the f lower freak as well. But so as such, it's just a map. And similarly, the other way around with the f lower sharp. So if f lower sharp, which is the left adjoining the L star exists, which is the case as we said for these movements, then we have f lower sharp. F upper star E tensor f going to E tensor f lower sharp. Okay, so again, a priori, there's no reason for this to be an isomorphism, but the again easy lemma is for H or so this was an abstract discussion here, and when I take this, when I apply to these Motivic spaces, then at least this here is an isom. And let's say and is weakly smooth, then this is an isom. This is no isom. Okay. Why? But again, you reduce yourself to the case of representables, and then it follows from the definitions. This one we will see next time. Then is not a general isomorphism. So in some sense, the first key step that we will have to do is if this net f is a closed embedding, then in fact it is an isomorphism, as we will see, and that will already use all the power of this localization theorem. And so you can think of this already as a non-trivial thing. Yeah. So yeah, I will encourage you to have a look at the notes if you want. So I skipped practically all the formal properties because they are a little bit, well, they're formal, let's say. Next time there will be the actual work will begin, namely we will prove this localization theorem, which is an honest non-trivial statement involving all these weakly smooth, weakly tall, and so on. Yeah, everything I did so far would have worked for any, I mean, basically any category of schemes and any tau and so on. Yeah, so this was really just to set it all up. But next time will be the non-trivial. Then after this, we will start talking about the stable non-trivial category and yeah, get the 6 numbers on there and go out from there.